In the previous lecture of Hamiltonian formulation, we have studied about phase space and the meaning of Hamiltonian function. Now we will discuss the most important concept of this topic, which is Hamilton's canonical equations. First of all, we will derive the Hamilton's canonical equations, and after that we will see the physical significance of the Hamiltonian function. So, as you have read in previous lecture that Hamiltonian of a system is a function of generalized coordinates, generalized momenta and time. So, we know that Hamiltonian H is a function of QK, PK, T. That is, H is equal to H of QK, PK, T. Or you may write it as this is H of Q1, Q2 up to QF, where F is the degree of freedom of the system. And just like that, P1, P2, so on, PF and T. Now I would like to find the infinitesimal change in this Hamiltonian to derive the Hamilton's equation. So therefore we can find dH. As you can see that h is not a function of only one variables, but it is a function of 2f plus one variable, independent variables. So we must follow the rules of partial differentiation. So what will be this result? This will be actually del h by del q1 dq1 plus del h by del q2 dq2 plus so on plus del h by del qf dqf. Now we will take the differential with respect to different phase, and so the terms will be del h by del p1 dp1 plus del h by del p2 dp2 so on plus del h by del pf dpf, and plus now we will take the differential with respect to t. So the term will be del h by del t dt. You can see that we can write the RHS in compact form by the use of sign of summation. So the terms in this row and in this row can be written in compact form by the use of sign of summation. And what will be that result? You can see easily that this is dH equal to summation over k, where k runs from 1 to f, but I am just writing here only k, and this is del h by del qk dqk plus summation over k del h by del pk dpk and plus del h by del t dt. Say this is equation 1. Now, as I have studied in previous lecture, the meaning of the Hamiltonian function h. So from that meaning we will also find dh. Now we have h equal to what? You have learned that h is defined as summation over k pk qk dot minus L, and this L is actually a function of qk dot and t. So now let us find dh from this definition of h. So we can write dh equal to what? See the first term. As in first term there is a product of two functions pk and qk dot. So we will follow the rule of differentiation of product of two functions. And from this what we will get? We will get that this is qk dot dpk plus summation over k pk dqk dot and minus dl. And let us say this is equation number 2. Now first of all we will find this dl, that is the infinitesimal change of Lagrangian, and then we will substitute that value in this equation 2. So now we know that this L is equal to L of qk dot and t. And so what will be dl? You can see I am just writing it in compact form directly as you have learnt it. This will be summation over k del L over del qk dqk plus summation over k del L by del qk dot dqk dot and plus del L by del t dt. Now, as you know that this dl by del L by del qk, del L by del qk, not del L by del qk dot. This is what? This is actually generalized momentum. You know this is actually pk, and del L by del qk. This is actually qk dot. This is del L by del qk is pk dot. Now let us substitute these two values in the above equation. So here del L by del qk will be replaced by pk dot, and this del L by del qk dot will be replaced by pk, and so the above equation will become what? We can write it easily. So the above equation will become dH equal to summation over k and let us see this equation. Del L by del qk, this will be pk dot, and this pk, first of all this will be pk dot, and del L by del qk dot, this is actually pk. So what will be our equation? Our equation will be actually pk dot dqk, pk dot dqk plus C again del L by del qk dot, this is pk, so this will be pk dqk dot. So this is pk dqk dot, and the last term is del L by del t dt. So this is plus del L by del t dt, and this is actually the value of dl, not of dh. So I have mistaken here, this is actually dl. Now we will substitute this value of dl in the equation number 2. So substituting this value of dl in 2, we get what we will get? We will get expression for dh, and this dh will be equal to what? This will be summation over k. See this equation. This is qk dot dpk plus pk dqk dot. So this is qk dot dpk plus summation over k pk dqk dot, and there is minus dl. Now we will substitute the value of this dl from here, and so this is minus summation over k pk dot dqk minus, this is summation over k pk dqk dot and minus del L by del T dt. Now see here, this pk dqk dot, these two terms will cancel out, and so the result left to us is summation over k qk dot dpk minus summation over k pk dot dqk and minus del L by del T dt. This is the value of dH, and say this is equation 3. Now you can see that there are actually two equations for dH. See the first equation here, that is equation number 1, which defines actually dH, and so we can compare the two equations 1 and 3, and after comparison we will find the coefficients of dqk, dpk and dt. So you may write that comparing coefficients of dqk, dpk and dt in equations 1 and 3, we will get, you can see it very easily, that we will get qk dot equal to del H by del pk and pk dot equal to minus del H by del qk, and del H by del T is equal to minus del L by del T. Actually, the set of these two equations is known as Hamilton's canonical equations. This is also an important equation, but this is not Hamilton's equation. So the equations in A are referred as Hamilton's equations or Hamilton's canonical equations of motion. And you can see that in case of a system of n particles, there are 6 n partial differential equations of first order in terms of rectangular coordinates in place of 3n Lagrangian equations of the second order, as I have discussed in the introductory lecture. So equations in 5 are known as Hamilton's equations. Or Hamilton's canonical equations of motion. If n be the number of particles in the system, then there are 6n partial differential equation PDE of first order. So this is the derivation of Hamilton's equations. You must remember these equations due to Hamilton, as we will directly use these equations in solving the problems based on the Hamilton's equation of motion. Now we will discuss the physical significance of the Hamiltonian function h. So now physical significance of h. I would like to discuss the physical meaning or physical significance of h in two headings. Actually, when Lagrangian of a system is not an explicit function of time, then Hamiltonian h is a constant of motion. It may then not represent the total energy, but it continues to be a constant of motion in that condition. So I would like to first discuss if the Lagrangian L is not an explicit function of time t, then Hamiltonian h is a constant of motion. Constant of motion. This is a very remarkable fact, and it signifies physically the Hamiltonian of a system. And first of all, we will prove this statement. As you know, Hamiltonian is a function of generalized coordinates and generalized momenta and time too. So we know h is equal to h of qk, pk and t. Therefore, we can find the total time derivative of this Hamiltonian h, that is dh by dt. So what will be this? Let us see by the rule of partial differentiation. Now I hope you are familiar with this process, so I am just writing in a short manner. So this is summation over k del h by del qk dqk by dt plus summation over k del h by del pk dpk by dt and plus del h by del t dt by dt, and this is, you know, del h by del qk. From Hamilton's equation we know that this del h by del qk is equal to minus pk dot. So this will be summation over k minus summation over k pk dot and dqk by dt. This is actually qk dot plus del h by del pk. From Hamilton's equation we know that this is qk dot. So this is summation over k qk dot and dpk by dt, this is pk dot. And here dt is 1, so this is del h by del t. And you can see that these two terms will cancel out. Remember, here I have used the Hamilton's canonical equation which just we have derived. This del h by del qk in accordance with Hamilton's equations is minus pk dot, and this del h by del pk is qk dot in accordance with the Hamilton's equation. So what we get here, you can see that dh by dt is equal to del h by del t. We have find it, and let us say this is equation 1. Now just in the derivation of Hamilton's equation, you see this equation number 4, where we have derived that this del h by del t is actually equal to minus del l by del t. So we can compare this equation with that. So, but we know that del h by del t is equal to minus del l by del t. So from equation 1 we can write that this dh by dt is equal to minus del l by del t. You can see it, minus del l by del t, and say this is equation number 2. Now if L is not an explicit function of time, then what will be this term? This term will vanish, this term will be 0. So you can write, if L is not an explicit function of t, then this del L by del T is equal to 0. And so in that condition, dH by dt will be 0 in accordance with equation number 2. And if dH by dt is 0, what does it refers? It refers that H is equal to constant. And this is the statement which I have written above. So you can see that if the Lagrangian is not an explicit function of time, in that condition, Hamiltonian of the system is a constant of motion. So this is its first physical significance. Now we will discuss the another important physical significance of the Hamiltonian. And the another most important physical significance of Hamiltonian is that the Hamiltonian represents the total energy of a system, but only when the system is conservative. And when you say that system is conservative, what do you mean? You mean that the coordinate transformation is independent of time. And so the another significance I would like to discuss is for a conservative system, H represents the total energy of the system. If the system is conservative, you note it, only then the Hamiltonian represents the total energy. That is, you may say that for a conservative system, H is equal to T plus V. You know T represents the kinetic energy of the system and V its potential energy. But this result will hold only when the system is a conservative system. So now I would like to prove this statement. You know the potential energy does not depend upon generalized velocity if the system is conservative. So for a conservative system, del V by del QK dot, this equal to 0. This is a very remarkable fact that, and you may call it, this is just a condition for a conservative system, that the potential energy V is actually position dependent, QK dependent, not QK dot dependent. And now from the definition of Hamiltonian, we have studied that H is equal to summation over K Pk Qk dot minus L. And we can write it summation over Q. This Pk, you know that Pk is defined as del L by del Qk dot. So I write instead of Pk, del L by del Qk dot into Qk dot minus L. And we can write this expression, that is expression for H, as summation over K Qk dot del Qk dot, and you know L means T minus V. So L is replaced by T minus V. And this is minus L. As we know that Lagrangian is defined as T minus V, where T is kinetic energy and V is potential energy. Now let us simplify this result to some extent. This is summation over K Qk dot, and we may write it as del T by del Qk dot minus del V by del Qk dot and minus L. And this equals summation over K Qk dot del T by del Qk dot minus L. Why? As we are considering that our system is conservative, and just I have mentioned above that for a conservative system del V by del Qk dot is equal to 0. So this term is 0, and hence our result is like this. Now we will write the expression for kinetic energy T of our system. So this is Qk dot del Qk dot, and what we will write for the kinetic energy T? We can write it summation over I half mi Qi dot square. Here actually I represents the total number of particles. This will run from 1 to n if n is the number of particles in the system, and minus L. And you can see from here that this will be summation over K half Mk Qk dot square minus L. I have written the limits for summation here by the index I, but you may change it to K. If we will differentiate this Qi dot square with respect to Qk dot, that is Qk dot square you may call it, then that will be simply Qk dot, and this Qk dot when will be multiplied, that will be Qk dot square. And what is this? Actually the half factor will cancel out, so here this will be actually 1. And what does it represent? Actually it represents the twice of the kinetic energy. So this will be 2T minus L. And we know that this L is actually T minus V, and so this will be simply T plus V. So therefore you can see for a conservative system Hamiltonian H is equal to T plus V. So you can say that for a conservative system where the coordinate transformation is independent of time, the Hamiltonian function H represents the total energy of our system. So these are the physical significances of Hamiltonian. In next lecture, we will see some of the important applications of Hamilton's equation.